Welcome to the 12th TA live interaction session for the NPTEL course Principles of Signaling Systems offered by Professor Aditya Jagannathan from IIT Kanpur. So this is the last regular TA session for this course in this semester. And uh, just a bit about myself. My name is Yashvanth, and presently a PMRF Ph.D. student at the Department of EC at IISc Bangalore. I work broadly in signal processing and wireless communications. If you have any doubts regarding the course contents that or the live interaction session contents that we do, please write to me in this email ID. And for this last regular session, we will be looking at filter delays and some realization structures. Note that this is the last regular session, but we will also be having one more session next in the coming week. That will be the final session summarizing all the topics that we have seen in this course. A very quick summary of everything, and also we will be solving some very interesting questions from all topics, prep, most preferably from all previous year gate questions. And I think the date for that session will be on 16th April. Okay, so that will be the last or the final session, live interaction session for this course. Okay, so as usual, let's get started with a summary for the week 12's lecture. So basically, we started with what is called the phase delay. Okay, so to understand that, what you do is you take an LTI system whose impulse response is characterized by h of t. Okay, you pass the input a cos omega naught t and look at the output. The output, you can show that if you take cos omega naught t as the input, then the output will be a times mod of h of omega naught times cos omega naught t plus phi of omega naught. That is, when let's say the input does not have any phase, but the output has some phase offset. The system is introducing some phase offset, and it is also amplifying the signals, or it is scaling the signal by amplitude scaling of mod of h of omega naught. Okay, so this is a homework. You can always show that this is always true for an LTA system. Okay, what you do, you just express cos omega naught t as a what? As a or by Euler's relation, express it as a complex exponential and use the eigenfunction property of the complex exponential of an LTI system. Okay, now what is this? Now what is phase delay? Phase delay is defined as the negative of phase offset divided by omega naught. That is the frequency. Okay, so this is defined as what is called the phase delay. Okay, so this basically represents the delay of the carrier input to an LTI system. Now, the next concept is what is called group delay. How was the group delay defined? So, let's say in addition to a carrier signal, you also pass a low frequency tone or a message. Right. So, for example, if you recall in the properties of Fourier transform, we studied something called modulation theorem, right? In our sessions. So, what we told is that we basically mount a small low frequency signal over a high frequency signal, and then you transmit that over the communication system, and that is what we call it as modulation theorem, and that is precisely what we are doing here also. So, suppose you, instead of just transmitting cos omega naught t, you also multiply that with a low frequency signal cos omega mt, such that omega m is much smaller than omega naught. So then basically this cos omega mt is what is called the message signal, and cos omega naught t is what is called a carrier signal. Okay, then you can show that if you pass this signal to an LTA system, the output can be written as same the product of the two cosinusoids, except that each cosinusoids will have its own phase offsets. So basically, whatever phase delay or phase offset you get corresponding to the carrier signal is what is called the phase delay. That is what we saw just above. Whatever is the phase offset you encounter for the message or the message signal is what is called the group delay. So group delay is defined as the negative derivative of phase response with respect to the frequency evaluated at omega equals omega naught. Okay, so around omega equal to omega naught, what is the differential change in the phase response as a function of frequency is what is called the group delay. So whereas if you look at the phase delay, you don't have the derivative. It's just the instantaneous, the ratio. But here it's a differential. It's a derivative of the phase response. Okay, where phi of omega is the phase response of system. So message signal is delayed by group delay, and carrier signal is delayed by a phase delay. Suppose if the phase response turns out to be a linear function of omega, that is a linear function of frequency, then what you can show is that group delay equals phase delay. That's because delay, if you that's because your phi of omega by omega is same as d of phi of omega by d omega whenever phi of omega is linear in omega. Okay, that's why group delay equals phase delay whenever the system exhibits a linear phase response. So that's basically about filter the group about delays, filter delays. Next, in fact, the rest of the session was on realization of IIR filters. That is, if I give you an impulse response, let's say I want to design a filter, and I know the filter is characterized by its own impulse response, right? Then basically the question is, how do I implement such kind of a filter? That is, what should I do physically? How can I implement? That is what is called realization. And in particular, we will look at what is called IIR. So what is IIR? It means that the system, that particular impulse response has infinite samples. That's called infinite impulse response filter. That is, if I take the h, for example, h of n. So this is the generally for a discrete time system is what we will be studying. So this in fact is for discrete, not for continuous time system. So that means if a discrete time system means impulse response is h of n, and this could either be a finite set or an infinite set, right? Because h of n is the impulse response. It could, for example, 1, 2, 3. Just three samples, or it could be 1, 2, 3, 4, and so on. It will keep on going till infinity. That is another. That these are two different types of simple impulse responses. Of a system whose impulse response is a finite sample duration is called a finite impulse response filter. That is called FIR. Whereas on the other hand, a system whose impulse response, a discrete time system whose impulse response is not limited, it is infinitely, the set is infinitely long, then that is called an IIR filter, that is infinite impulse response filter. Okay, in particular we will study about infinite response filter. That is because for an IIR filter you can always decompose your h of z as a proper ratio, or a ratio of two polynomials, p of z and d of z. Okay, h of z is here is a transfer function, that is the z transform of the impulse response is called the h of z. You can always express it as a ratio of two proper polynomials, p of z and d of z. The zeros of d of z is called the pole, and zeros of p of z is called the zeros of the filter. Okay, so that's what I've written here. H of n is not time limited. Example, if we say h of n equal to minus 1 power n, that is for n equal to 0, you have plus 1, n equals 1 minus 1, n equals 2 plus 1, n equals 3, minus 1 power 3 is minus 1. So it keeps on alternating between plus and minus 1 and keeps on going. It doesn't stop at some point because n keeps on changing, n keeps on going, right? So basically for every n, you have some non-zero value. So this system whose impulse response is minus 1 power n is a IIR filter. It's said to be an IIR filter. Okay. So IIR filters. The first type of realization is what is called direct form 1 realization. So what we do in this direct form 1 realization is you express your h of z as a ratio of two polynomials. So the numerator polynomial is called P naught. So these can be written as P naught plus P1 z power minus 1 and so on till. So let's say there are only three. Let's say there are only three coefficients. It's a third order polynomial plus P3 into z power minus 3. Similarly, you can write the denominator as 1 plus d1 z power minus 1, d2 z power minus 2, and d3 z power minus 3. Okay, this the numerator I call it as P of z, and denominator polynomial I call it as d of z. So you can write your h of z as the product of two functions. One is p of z into 1 by d of z. Okay, so you have split your transfer function into two factors. Now what I will do is, essentially, I will first pass my input to p of z, get the output as, let's say, w of n, that is called w of z, and pass the input w of z to another system whose impulse response is 1 by d of z, and finally get the output y of n. Okay, that's what I'm doing. So basically what I'm doing is, you take the input x of n and you pass it through the first block, whose impulse response is, whose transfer function is p of z. You got an intermediate output w of n, and pass w of n through another filter whose impulse response is 1 by d of z. Okay, and then you get finally y of n as output. That's what I wrote it here. So x of z, you pass it through p of z, then pass it to 1 by d of z, and that will give you y of z. That's because why should this happen? That's because if you write down the overall signal at the receive at the output, y of n equals convolution of all the three blocks. X of n convolve with p of n convolve with q of n, where q of n is such that q of z equal to 1 by d of z. Right. Now, basically, what you can do is you can do commutativity property. So replace Q of n and P of n. So Q of n comes first and P of n comes later. This is because of commutativity property of convolution. That means if this is a time domain, that means by using the convolution property of Z transform, that means in the frequency in the Z transform, you just multiply the individual Z transform. So Y of Z is nothing but X of Z into 1 by D of Z into P of Z. Okay, so I mean, this is basically for the second version. We will see that in the next. But all I'm trying to say is that if you just do this much, right? If you just split into two things, P of Z and D, 1 by D of Z, you can still recover your Y of n. And now, basically, the question is, how do I implement this structure? How do I implement this structure? Correct. And basically, for the crux is that you need to implement two different structures. W of Z equal to X of Z into P of Z. That is this structure. And y of z is equal to w of z into 1 by d of z. That is this structure. Okay, we will see example why this it should come like this. Okay, here what is the z inverse? Z inverse nothing but this z inverse, and these triangles are nothing but the amplitudes. That is p1, p2, p3. Okay, that is this p naught is basically this one, p1 is this one, and p3 is this one. Okay, and similarly, if you have d1, d2, d3, it will come minus d1, minus d2, minus d3, and then you need to implement this kind of a structure. So this is what is called the direct form 1 realization of your IIR filter. Now, what is direct form 2? What you do is very simple. Instead of passing it through P of Z first and then passing it through 1 by D of Z, you flip it because of the convolution property of commutative property of convolution. That is, you first pass it through 1 by d of z and then pass it through 1 by and then pass it through a system with the transfer function p of z and get y of z output. Okay, so if you do that, what you can do is that you can simplify your representation, and that is what is given by this figure here. Okay, we will with using an example, we will see how to realize all these filters. In fact, given a direct form 1, how to find the direct form 2 structure. You can directly find, we will see those kind of tricks in today's examples. Similarly, if you are given direct form 2, how to obtain direct form 1 realization. Okay, that is about direct form. Okay, so what is the advantage of direct form 2 is that it requires only half the number of delay units. So the z power minus 1 is nothing but we call it delay unit. That's because if you remember z power minus 1 come in the frequency domain or the z domain if you have x of n minus 1. If you do x of n minus 1, the corresponding z transform is z power minus 1 into x of z, right? That means if you do a delay by 1 unit in the time domain, that means it is equivalent to passing it through a delay unit represented by z power minus 1. That's why z power minus 1 is basically also called as a delay unit. Okay, so what we are saying here is that your direct form 2 requires only half the number of delay units compared to direct form 1. So you see, for example, you look at this a very, very simple example. Here you needed 1, 2, 3, 4, 5, 6. You needed 6 delay units. Whereas if you look at this direct form 2 realization, it's only 1, 2, 3. You require only 3 delay units. So exactly half of what you need for direct form 1 is what you need for direct form 2. Therefore, direct form 2 is a much efficient way to implement your IIR filter. The next is what is called the transpose form. Not much different again. Basically, what it says is that it's just again the way you view your signal. Okay, that basically that you can write y of z is nothing but x of z into h of z. But h of z is nothing but 1 by d of z into p of z. That's what we saw before. Now, what I do is I'll call x of z into 1 by d of z as w of z. So I now have two kinds of relation, namely that x of z into 1 by d of z equal w of z, or in other words, x of z is equal to w of z into d of z. That is 1 by d of z, take it to other side, right hand side. This is the first equation. The second equation is that y of z is equal to w of z into p of z. That is the second equation. You implement these two equations separately, and then you pass, and then you get the output. So it turns out that this structure is slightly different from whatever structure you had derived in the direct form 1. Okay, you can see it very clearly. It's just that slight differences in the structure, but all of them will simply implement the same operation in the end at the end of the day. So that is called direct form 1 in transpose. What is direct form 2? Basically, it's like again you do the same thing, but with basically what you do, you interchange this to the left block and interchange this left to the right block. That becomes direct form 2. So if, for example, what I mean is that now let's zoom out a bit. You see, this is direct form 1 realization. This is direct form 2 realization in the non-transpose form, the original form. You see, what I essentially did is you take this second block and bring it to the first block. You take the first block and bring it to the second block. Okay, if you do that for the direct form 1, you get direct form 2. See, you have all these P1, P0, P1, P2, P3 sitting in the right side, and minus D1, D2, D3, D3, D3 sitting in the left side. And what you can show is that these delay units will now come at the same in the middle. And that's why you can club both the delay units from both the side into a common delay unit in the direct form 2. That is the reason why direct form 2 requires exactly half the number of delay units compared to direct form 1. Is this clear? I mean, is the trick clear how to obtain direct form 2 from direct form 1? Huh, good. That is what I'm going to do for transpose structure also. So this was your transpose structure. So bring the left to the right and right to the left. And that's what you get, transpose for the direct form 2 structure of the direct form 2 realization of the transposed for realization. Now it's cascade realization. Again, simple to understand. Cascade means you have number of things going on in cascade. So let's say your h of z is given by p of z by d of z. You decompose this as the into product of two other transfer function, that is p1 of z by d1 of z into p2 of z by d2 of z. Now p1 of z by p. So basically, okay, the first one is p, not h1, that is h2. That means you can treat each one of them as individual filter, and then you need to multiply. That means the output of one should be passed as input of another filter. Okay, so what you do, simple. You take x of n, construct the direct form realization of p1 of z by d1 of z, and that will be nothing but h1 of z, and pass that output to another function, another filter, which is the direct form realization of p2 of z by d2 of z, and obtain output y of n. This is what is called the cascaded form. Okay. Now parallel realization. So this is called a cascaded realization. Now what is parallel realization? So parallel realization. In parallel realization, what we do is you first do a partial fraction expansion of p of the h of z equal to p of z by d of z. You can always write it as some from gamma naught plus gamma 1 by 1 plus alpha 1 z inverse, and another, let's say another. It's just an example for a third order filter. Okay, h1 of z plus h2 of z plus h3 of z. That means what, all of them have to be parallelly executed. So what you can do, you take x of n, you divide this into three branches. Here three because you have decomposed it into three terms. And then implement each of these filters separately. So h1 of z is just having gamma naught. That means it just multiplies by gamma naught. The output is h1 of z. Some input. Some output will come out of this. Then do direct form realization of the second filter. Then parallelly do direct form realization of third filter. Take the output of all of them and add them up. That's because that is because of the addition in the partial fraction expansion. And then you add all of them and get the output. So this is called parallel form because the operations are happening parallelly across three different branches. Okay, this is called parallel form 1. Parallel form 2, what you do is you have to do the same thing, except that you take a partial fraction expansion containing the term z instead of z inverse. That will slightly give you a different expression for or different way to realize your system. That's all. So what we have seen, there are several ways to implement. First way is what is called the direct form 1 realization. And then we saw direct form 2 realization. And we saw that direct form 2 realization is a much efficient way to implement a filter compared to direct form 1. Then we saw the transpose structure of with respect to direct form 1 and direct form 2. And then we saw was cascaded form of filter realization. And finally, we saw parallel form 1 and parallel form 2 for IIR filter realization. Okay, so these are the different types. So in fact, any kind of implementation will give the same output y of n for any given x of n. If you have a given h of z as a transfer function, for any x of n, all these different structures, different ways of implementation should yield the same answer. It's only the way in which you compute the operation differs across all these types of realizations. So I think this is what is summary for this week. Are there any doubts? Okay, good. There's no doubt. So that basically is the first part. And the second part of today's class will be tutorials. Okay, so we will look at some examples. The first question goes as follows. The input to a channel. So channel here is like a system. Okay, assume it to be a system. Input to a system or a channel is a band pass signal. Band pass means what's a high frequency signal? It is obtained by linearly modulating a sinusoid carrier with a single tone signal. The output obtained by passing it through an LTI system is y of t. They have given, so basically what they're saying is you have a modulation done, that is you modulate or multiply a carrier signal with a single tone message signal, and you pass that through an LTI system. You got an output, and the question is giving you what is the output. Output is given by y of t equal to 1 by 100 times cos 100t minus 10 power minus 6 into cos 10 power minus 6t minus 1.56. Question is find the group and phase delay. Okay, so what you need to do, first write down the general expression for your um, what your general expression for the output when you pass modulated cos signal as an input, right? So general expression is what? Y of t equal to a mod h omega naught into cos omega mt minus phi m into cos omega naught t minus phi naught, right? So omega m is nothing but the message frequency, and omega naught is a carrier frequency. And what we also know is that omega m is much smaller than omega naught. You look at the expression. The first one is having 100, second one is having 10 power 6. 100 is a much smaller number compared to 10 power 6. Therefore 100 should be your message frequency, and omega 10 power 6 should be your carrier frequency. As a result, the phase offset for your message signal is given by 10 power minus 6, and the phase offset corresponds to carrier frequency is 1.56. Now, what you should do, you should take omega m common, because that's how we had defined our group and phase delay, right? So take omega m common. That means you can write the output as y of t equal to 1 by 100 of cos of 100 common t minus 10 power minus 8. That's because if I multiply 100 by 10 power minus 8, I get back 10 power minus 6. Therefore, you need to multiply by 10 power minus 8 times cos of 10 power 6, you take common, 10 power 6 of t minus 1.5 into 10 power minus 6. That's because if you multiply 1.56 into 10 power minus 6 by 10 power 6, you get 1.56. Okay, and now what did we say? We said that 10 power minus 8 is a group delay, and whatever is the term for message carrier signal is called the phase delay. Therefore, group delay is 10 power minus 8 seconds, and phase delay is 1.56 into 10 power minus 6 seconds. Is it clear? Okay. The next question is, find the group and phase delay for the following systems. So the first system is the impulse response given by delta of t minus t naught. Second system whose impulse response is e power minus t by rc into u of t. U of t is a unit step function. So what should we do? We need to first find a phase response system. That is the first thing. For phase response, what we need to do, first find the transfer frequency response. So h of t is equal to delta of t minus t naught. Take the Fourier transform, that will give the frequency response system. So for delta of t minus t naught, by applying time shifting property of the Fourier transform, you get e power minus j omega t naught. That is your frequency response. Now for phase response is what? Angle of e h of omega. What is angle of h of omega? Just minus omega t naught, because this is of the form e power j theta, whose angle is nothing but theta. Therefore, phase response is given by f of omega equal to minus omega t naught. Okay, that's the we got the phase response. That is the first thing. Now obtain the group delay. What is the group delay? Minus d by d omega of phi of omega at omega equals omega naught. That is minus d by d omega of omega t naught, because that is your phi of omega at omega equals omega naught. That is nothing. This is nothing but just t naught. Okay, so this minus and minus will get cancelled, so it's just t naught. So the group delay is equal to t naught. Similarly, if you look at the phase delay, that is just no differentiation is there in that expression for the phase delay. So it's just minus phi of omega naught by omega naught, which is nothing but minus of minus omega naught t naught by omega naught, which is equal to t naught. Okay, therefore here you see both of them are equal. That's because your phase response is linear in your frequency, and that's what we told, right? Group delay and phase delay are equal when the phase response is linear. That's why both group delays and phase delays are matching. Okay. The next question is for the impulse response e power minus t by RC into u of t. So basically, you recall that your Fourier transform of e power minus at into u of t is given by 1 by j omega plus a. So here a is nothing but 1 by RC, right? Therefore, your Fourier or the frequency response of the system is given by h of omega equal to 1 by j omega plus 1 by RC. Okay, so what is now the angle? What is the angle of h of omega? So this is nothing but it's a ratio of two terms. So then the angle will be angle of one, that is the numerator, minus angle of the denominator. Because when I divide two numbers, their angles will be subtracted. Right. Now, but one is a real number, right? So there is no angle for a real number, so angle is 0. But for the second one, what is the angle? So what is this? This is a purely an imaginary number. This is a complex number. Therefore, angle is nothing but tan inverse the imaginary part, which is omega, and the real number 1 by RC. Therefore, the angle of j omega plus RC is given by tan inverse, is given by tan inverse omega by 1 by RC, or 1 by RC comes up, it becomes tan inverse omega RC, but there's a minus. So angle of h of omega equal to minus tan inverse omega RC, which is equal to phi of omega. Is it clear till this point? Okay, great. Now we got the expression for phi of omega. That means what is phase delay? Phase delay is something but minus phi of omega naught by omega naught. So minus and minus cancel. So it's just tan inverse omega naught RC by omega naught. That's all. We cannot simplify this further. What is group delay? Minus d by d omega of phi of omega at omega equals omega naught. That is, you differentiate minus tan inverse of omega RC at omega equal and put omega equal to omega naught. Okay, but you know that what do we know? We know that d by dx of tan inverse x is nothing but 1 by 1 plus x square. That's basically our expression for tan inverse x, right? But now you have to apply chain rule also, because it's not just x, it is something like ax. So you need to write a also. Maybe I can write that here, no problem. Tan inverse of ax is nothing but a by 1 plus ax square, a square x square. Okay, so here a is nothing but RC, because they're differentiating with respect to omega, which is like x. Therefore, you have RC by 1 plus omega square r square c square, and put omega equal to omega naught. Therefore, if omega square becomes omega naught square. So this is the expression for group delay. Is it clear? Okay. That's about the this question. The third question is now that these were the two questions from the filter delays viewpoint. Third question is from now onwards we will look at the direct form and the filter realizations using direct forms, cascaded forms, parallel forms, and so on. Question is, let h of z be this number 1 plus 2z inverse divided by 1 minus 3z inverse plus 2z power minus 2. Question is, find the direct form 1 and 2 realizations. Great. So direct form 1, let's start with direct form 1. Direct form 1, what is basically h of z is nothing but this, which can be written as p of z over d of z. What we told in direct form 1 is that you pass x of z through p of z first. You get the intermediate signal w of z. and pass that through another filter with whose transfer function is 1 by d of z, and you get the output y of z. Okay, so this is what is essentially happening, right? First you implement the output for w of z, and then implement the output for y of z. You connect both of them. That is your end-to-end direct form 1 realization. So let's implement block A first. That is x of z into p of z is equal to w of z. Correct. Now that means what? What is p of z? 1 plus 2 times z inverse. So x of z into 1 plus 2 z inverse equals w of z. Okay, that is nothing but x of z plus 2 into x of z into z inverse equals w of z. Or in other words, in the time domain, by applying the time shifting property, it is nothing but x of n plus 2 into x of n minus 1 equals w of n. Now just implement this in block form. But is what you're saying is w of n is nothing but you find x of n plus 2 times its delayed version. So you take x of n, you multiply it by 1. Take x of n, you delay by 1 unit, that is nothing but by z inverse, and then multiply it by 2. Add both of them, you get w of n. Okay, so I've implemented this using this structure. Is this clear until now? Okay, great. Now what is the second block? To implement w of z into 1 by d of z is equal to y of z. That means what is 1 by d of z? D of z is nothing but 1 minus 3 z inverse plus 2 z power minus 2. So 1 by that is nothing but 1 by this number. So w of z into 1 by d of z is equal to y of z. That means what? You take this number to the right hand side. So what you get is w of z is equal to y of z minus 3 times z inverse y of z plus 2 times z power minus 2 y of z. Or not, or bring this second and third term to the left. That is w of z plus 3 times z inverse y of z minus 2 times z power minus 2 y of z equals y of z. So you need to implement this equation. What it says is you just observe it very carefully. You have w of n as the input. You pass this through some addition. Let's see what are the other terms for the addition, and you get y of n. Take a part of y of n, delay it by 1 unit. That will give y of n minus 1. Correct? And now take a part of it. Basically, what you do, you multiply it by 3 and then add it with the w of n. Take another part of y of n, y of n minus 1, again delay it, which becomes y of n minus 2, and multiply it by minus 2. So it becomes minus 2 times y of n minus 2. Now add all of them together. So it becomes what? So basically at the output of this adder, you have 3 of y n minus 1 minus 2 of y n minus 2. Add this to w of n, and that will be your y of n. Is this clear? Yeah. So it's just a mere implementation of this case. Now, so what I have implemented B block also. So I have implemented A block, which takes x of n as input and gives w of n as output, and B block, which takes w of n as input and gives y of n as output. Now just connect both the blocks. Connecting both, you have x of n, you pass that through the first block, and then the output of that is passed to the second block, and the output of the second block is y of n. That's all. This is basically your direct form 1 realization of the given the filter with the given transfer function. Now to obtain direct form 2 realization, simple. You interchange this. This is basically your A block, and this is your B block, right? So you interchange A and B block. So what do you see? See, I have written down that here, right? So first x of n is there, and then you pass it to the first B block here. Exactly same. Now no difference. Adder is there, plus 3 and minus 2 addition, z inverse, z inverse. Exactly the same. And the A block is now going to the second. That means just z inverse plus 2 and adder. Okay, just interchange both the first and second block. And then what you do, you club all the common delays by just one delay. You don't need, because it's the same signal, you're delaying with different delay units. Just use a common delay unit. So it just clubbed to a single delay unit. Okay, and this becomes direct form 2 realization. Is this clear? That's also, if you know direct form 1, you can obtain direct form 2. Similarly, if you know direct form 2, you can always obtain direct form 1. That is what you do. You know that there is a common delay. You split this into two different delays and obtain this. And then again do an interchange of these both. You will get back direct form 1. So are all these clear? Okay, great. Now the next question is, for the same question in question 3. What is question 3? The previous question. Obtain the cascaded realization of the system. Cascaded form. Great. So what we will do, this is the given h of z. 1 plus 2 z inverse by 1 minus 3 z inverse plus 2 times z power minus 2. What I will do is now I will do a cascade realization. So what I will do, first, as much as possible, I will only realize I told, right? So here, if you go back to the general structure for cascaded form, this is what we told for cascaded form, right? So I want to implement this using cascade of, let's say, example H2 and H1. You try your best to implement each H1 and H2 as a first order. That is, it only contains z power minus 1. So that each of the implementation of each one of these becomes easy. Then you just have to cascade all of those filters. Okay? Fine. So you can write the denominator as the 3 z inverse, you can split it as minus z inverse minus 2 z inverse. And you can factorize the denominator as 1 minus z inverse into 1 minus 2 z inverse. So therefore, you can write your h of z, you can split your h of z as a product of two forms, h of z into h1 of z into h2 of z, where h1 of z is 1 plus 2 z inverse by 1 minus 2 z inverse, and h2 of z is 1 by 1 minus z inverse. Okay. Now, now basically all it remains is implement both of them separately, and then you connect both of them. That's all. So let's implement 1 plus 2 z inverse by 1 minus 2 z inverse first, h1 of z. That means the intermediate signal, call it y w of n, that is the output of h1 of z block, is call it w of n, which is a convolution of x of n and h1 of n, or w of z is equal to x of z into h1 of z. Right, therefore w of z is equal to x of z into 1 plus 2 z inverse by 1 minus 2 z inverse. Take the denominator 1 minus 2 z inverse to the left hand side. So it becomes 1 minus 2 z inverse into w of z equals 1 plus 2 z inverse into x of z. That means what? You take w of z, and that is w of z minus 2 z inverse w of z equals x of z plus 2 z inverse x of z. Okay, what it says is simple. Basically you let's say you take the input x of n and apply this operation x of z plus 2z x z inverse x of z. Whatever is the resultant signal, that signal should be equal to what you obtain by doing the operation y of w of z minus 2z inverse w of z. That's what I'm going to do. So I'll implement this right hand side separately here. That is, you take x of n, you first pass one x of n as is in the top branch. Second branch you delay by 1 unit and multiply by 2 and then get the sum. So basically here your b of n, the intermediate signal, will be nothing but x of n plus 2 times x of n minus 1. And now what is it? That should be equal to the signal that you obtain by having w of n minus 2 times w of n minus 1. So you have w of n, take a delayed version, that is w of n minus 1, you multiply by 2. That becomes 2 times w of n minus 1, add both of them. Whatever is the signal there, that should be your b of n, and that should be equal. Okay, so is this implementation clear? Okay, so the question is your question is, but when we interchange the signal, we are delaying is no longer simply y of n. So I didn't follow your question. Here I'm not having any y, right? I only have x and w. Okay, direct form 2. Okay, previous question, I guess. Okay, let's go back to the previous question. And the question is, when we interchange the signal, we are delaying is no longer simply y of n. I actually did not quite follow the question. Okay, let's say you interchange the blocks. Yeah, let's say you had two blocks A and B. You interchange them. and you get this, correct? And then you are saying, okay, here I did a y of n minus 1, but here I'm not having y of n minus 1. Is that what you're asking? Yeah, no problem. That's what I'm saying. No problem. It need not be. But all that you need to ensure is, in at the end of the day, whether this entire structure is giving you the correct y of n, which is equal to this entire structure. It's absolutely true that whatever whatever operation direct form 1 is doing should be done by direct form 2. No, it need not be the case. But let's say that you consider this whole structure as one h2 of, let's say, h of z, and this whole structure as another h of z. Both these filters should give the same output for any given input. As long as that happens, then don't worry. Here I do agree that you are delaying your output 2 times and then you implementing filter, but here you don't do, but that's okay. All what matters is you should get the correct y of n for any given x of n from both direct form 1 and direct form 2. As long as that happens, you need to worry. The implementations are going to be different. Is it okay? Okay, good. Fine. So this is what we have implemented for h1 of z. Okay, so you get x of n and w of n, and intermediate you implement this guy. For h2 of z, what do we do? W of z is given as input to h2 of z, and that gives output y of z. Okay, that means what? Your h2 of z is nothing but 1 by 1 minus z inverse. So that means you take 1 by 1 minus z inverse to the right hand side. So what you get is y of z minus z inverse into y of z equals w of z. Right? Because it's 1 minus z inverse and multiply y of z. So you get this term equals w of z. That means what? Y of n minus y of n minus 1 equals w of n. Or y of n equals w of n plus y of n minus 1. That's simple. Take y of n, pass it through an adder. The first chain will give y of n. Take a part of y of n, delay it by 1 unit, and then multiply it by 1 and add it with w of n. So this, if you look at the output, the y of n is nothing but w of n plus y of n minus 1. Okay, so we have implemented second part. Now all you need to do is just connect both these blocks, this guy and this. Connect both of them, you will get this. So you have x of n. First, this is basically your h1 of z, and this is your h2 of z. You get y of n for any given x of n. Okay, in fact, you can do slightly better also, because this was your direct form 1 realization. What you can do is you can flip. That is, you within the direct form 1, you can bring this to the left and bring this to the right. So that you will have a common delay unit and you merge them together, z inverse. Okay, so this becomes a more efficient implementation of the top. Is it clear? Is this the solution for cascaded form? Okay. The next question is, for the same system, obtain the parallel forms 1 and 2 realization. Okay, parallel forms 1 and 2. So what we will see is that first the solution for parallel form 1. So for parallel form 1, what you need to do, remember you need to do partial fraction expansion with respect to z inverse. Okay, so your given h of z is nothing but 1 plus 2 z inverse divided by 1 minus z inverse minus 2 z inverse plus 2 z power minus 2. Okay, divided basically what I did is I expanded this denominator like this. Now again do expansion, factorization, you get 1 plus 2 z inverse into 1 minus 2 z inverse into 1 minus z inverse. Same as what we did for our cascaded form realization. You see, cascaded form also we first did this only. You see, we got this. But the approach we took from here is that we decomposed this into 2 different filters, H1 and H2, and then we implemented both of them and connected both of them. But now the approach is, you don't do that. Instead, you take this fraction and do a partial fraction expansion of them. So it is basically it has 2 simple poles. All right, so you have 2 simple terms, A by 1 minus 2 z inverse plus B by 1 minus z inverse. How to find A? H of z into 1 minus 2 z inverse evaluated at 1 minus 2 z inverse equal to 0. That is for evaluated at z for which 1 minus 2 z inverse goes to 0. That is nothing but 1 minus 2 by z equal to 0 or z equal to 2. So you need to evaluate this h of z into 1 minus 2 z inverse at z equal to 2. Whatever is the answer, that is the value for E. Let's do that. So h of z into 1 minus 2 z inverse at z equal to 2 is nothing but 1 plus 2 z inverse by 1 minus z inverse into 1 minus 2 z inverse into 1 minus 2 z inverse. So this and this second term and 1 minus 2 z inverse will get cancelled. So what will be left out is 1 plus 2 z inverse by 1 minus z inverse at z equal to 2. So that's nothing but 1 plus 2 by z into 1 minus 1 by z at z equal to 2. This is nothing but 1 plus 2 by 2 divided by 1 minus 1 by 2. That is nothing but 2 by 2 is 1. So it's 2 by half, which is equal to 4. Therefore, your A is equal to 4. Now for B, what do? We take h of z, multiply by 1 minus z inverse and evaluate it at z, for which 1 minus z inverse goes to 0. Or that is nothing but z equal to 1. Because if I put z equal to 1, z inverse is also 1. So 1 minus 1 becomes 0. Therefore, h of z into 1 minus z inverse is nothing but h of z into 1 minus z inverse. And the z 1 minus z inverse will get cancelled. So what you're left out is 1 plus 2 z inverse divided by 1 minus 2 z inverse at z equal to 1. So that is nothing but 1 plus 2 by 1 minus 2. So that is nothing but 3 by minus 1, which is equal to minus 3. Therefore, your partial fraction expansion is nothing but h of z equals to 4 by 1 minus 2 z inverse minus 3 by 1 minus z inverse. Okay, so you have decomposed, instead of productified version as in the cascade form, you have now decomposed h of z as sum of two other filters, which is h1 of z given by 4 by 1 minus 2 z inverse plus h2 of z given by minus 3 by 1 minus z inverse. Right, so you can realize therefore your realization your structure should be x of n. You sample it two times. In the upper block, it should pass through h1 of z. In the lower block, it should pass through h2 of z. Take the two outputs from both the blocks, you sum it up, and whatever is the answer, that is your y of n. So all remains is how to implement h1 of z and h2 of z. Again, implement it using simple direct forms. So h1 of z is nothing but 4 by 1 minus 2 z inverse. And what do we know? Let's call this intermediate signal as y1 of z. And sorry, y1 of n. And this is y2 of n. Therefore, sum is nothing but over y1 of n plus y2 of n. So let's say y1 of n or y1 of z is nothing but x of z into h1 of z by convolution property. Therefore, y1 of z is nothing but h of z into 4 by 1 minus 2 z inverse. Just writing the expression for h1 of z. And now what you do, you take this 1 minus 2 z inverse to the right hand side. So what you get is y1 of z minus 2 times z inverse into y1 of z equals 4 times x of z. Okay, and that's nothing but then you take the second term from the left hand side to the right hand side. So it becomes 4 times x of z plus 2 times z inverse into y1 of z equals y of z. That means what I do, so take x of n, you multiply that with 4. Okay, and then you add it with some other number. We'll see what is that some other number, and the output is given by y1 of n. Take a part of y1 of n, delay it by 1 unit, and then you multiply by 2 and give it addition to the 4 times x of n. Okay, therefore what you get is 4 times x of n plus 2 into y1 of n minus 1 equals y1 of n. That is what is this equation in the time domain. So this is so basically for a given x of n, y1 of n is obtained by this h1 of z. Is this clear? Okay, it is clear. Now, what is left out is realization of h2 of z. So for h2 of z, what we know is that the output of h2 of z is given by y2 of z, which is again x of z into h2 of z. And h2 of z is nothing but minus 3 by 1 minus z inverse. Fine. Now again, bring this 1 minus z inverse to the right hand side. So what you get is y2 of z minus z inverse into y2 of z equals minus 3x of z. Or y2 of z equals minus 3 times x of z plus z inverse of y2 of z. So same thing as above, you take x of n and multiply it by minus 3, and to that you add y2 of n minus 1 multiplied by 1. That is equal to y2 of n. Therefore, for a given x of n, you can obtain y2 of n by passing through this h2 of z. So you have implemented h2 of z also. Is it clear? Okay, great. Therefore, now we have implemented both h1 of z and h2 of z. So combine both. So you have x of n. The top block implements h1 of z. You get y1 of n. Similarly, the bottom block implements h2 of z. You get y2 of n as output, and you add both of them, you get the net or the final output y of n. So this, whatever is the block sitting between x of n and y of n, is the parallel form 1 realization of the given transfer function or the given system with the given system with the given transfer function. Okay. The second question is parallel form 2 realization. So what the only difference is what we told is do partial fraction expansion with respect to z. Don't do with respect to z inverse. That is what we need to do. So the first step only differs. Once you have gotten the partial fraction expansion with respect to z, everything else will remain the same. You need to implement each of those blocks. So what we do, so there is z inverse everywhere. Okay, you need to do partial fraction with respect to z. Now, what is the highest degree? Denominator has the highest degree. So you take the it is grows in z power minus 2. Therefore, what you do, you multiply and divide by z square on numerator and denominator. Okay, therefore, if you do, what happens? Let's see. So what happens is you get z square of 1 plus 2z inverse divided by z square of 1 minus 3z inverse plus 2z power minus 2. Therefore, z square into 1 becomes z square into 2z inverse becomes 2z. That is for numerator. For denominator, z square into 1 is z square into 3 minus 3z1 becomes minus 3z, and z square into 2z power minus 2 becomes just plus 2 because 2 and 2 from the exponent will cancel. Okay, this is our partial fraction. This is our transfer function in terms of z, not in terms of z power minus 1, z inverse. Now do a partial fraction expansion of this function. So this can be, so numerator you can factorize it as z into z plus 2 divided by z square minus 3z plus 2. But remember, for partial fraction expansion, you want to take improper fractions, right? That is your proper fractions. You should not have improper fractions. That is, a degree of denominator should be more than degree of numerator. But here they are equal, z square coming. So what you do, you divide divide the numerator and denominator to get a proper fraction. So what I do, z square plus 2z, you divide by z square minus 3z plus 2. So z square, the coefficient is 1, therefore 1 times it goes. If I multiply 1 times z square minus 3z plus 2, I get z square minus 3z plus 2. Now subtract both of them. So z square and z square will cancel. Minus 3 will become plus 3, so 2 plus 3 will become 5. And plus 2 will become minus 2, you get 5z minus 2. Therefore, this is nothing but quotient theorem. So what do we know is that your dividend equals to divisor into quotient, theorem of division, right? That what is it? This is basically this, whatever is inside is called dividend, and this is your divisor, 1 is your quotient, and remainder is 5z minus 2. Therefore, you can write your h of z, right? That is nothing but this number. Okay, so maybe I'll write one step before coming till here. So therefore, I can write z square plus 2z is nothing but 1 into z square minus 3z plus 2 plus 5z minus 2. Now, what you do, you divide by z square minus 3z. Okay, you divide by z square minus 3z plus 2 on both sides. If I do this, what happens is this becomes z square plus 2z by z square minus 3z plus 2. That is nothing but h of z. That's why I wrote h of z. So z square minus 3z plus 2 will cancel the first term. That's why it's 1. Second term, 5z minus 2 will just get divided by z square minus 3z by plus 2, which can be factorized as z minus 1 into z minus 2. Is this clear? This h of z, is this clear? Okay, very good. Therefore, now what I will do, leave the 1. I will just do partial fraction expansion of psi z minus 2 divided by z minus 1 into z minus 2. So again, it has just simple poles. Therefore, you can write it as a by z minus 1 plus b by z minus 2. Okay, what is a? The 5z minus 2 by z minus 1 to z minus 2 into z minus 1 evaluated at z equal to 1. Therefore, z minus 1 cancels. What you have is, and put z equals 1. Then you have 5 minus 2 by 1 minus 2, which is minus 3. And similarly, the value for b is something but 5z minus 2 by z minus 1 into z minus 2 into z minus 2 at z equal to 2. Z minus 2, z minus 2 cancel, so put z equal to 2. So it becomes 5 into 2 minus 2, that is 10 minus 2. New in denominator becomes 2 minus 1, that is 1. So therefore, so it is equal to 8. Therefore, you have this 5z minus 2 by z minus 1 into z minus 2 as minus 3 by z minus 1 plus 8 by z minus 2. Therefore, from this expression, h of z is equal to 1 minus 3 by z minus 1 plus 8 by z minus 2. Until now, is it clear? Okay, great, it's clear. Now what I will do, that's all. I need to now see, I have decomposed this into 3 parts. What did I do? 1 is one part, minus 3 by z minus 1 is another part, 8 by z minus 2 is another part. So you need to parallelly implement all these 3 filters. Okay, for implementation, we have z minus 1 because we only have delay unit in implementation. Therefore, what you do, this 3 by z minus 1, okay, I will do one thing. Here, for the second term, multiply and divide by z power minus 1. It's because the highest degree of z is 1 in across denominator and numerator z. Therefore, I'm just multiplying and divide by z power minus 1. And what happens is 3 will become 3 z inverse. Z will become just 1 because z into z minus 1 is 1. And minus 1 will become minus z inverse. Similarly, the second term also you multiply and divide by z inverse. So the 8 by z minus 2 will become 8 z inverse divided by 1 minus 2 z inverse. Therefore, I need to implement all these 3 blocks and add them up. That is the parallel form 2 realization of the given transfer function. So the first block is simple. H1 of z is nothing but 1. That is, it just passes the input as output. It does nothing. Take x of n, multiply by 1 and pass it y of n. This is your H1 of z implementation. H2 of n implementation is take x of n, pass it through H2 of z and get y2 of n. That means y2 of z should be equal to x of z into H2 of z. But H2 of z is nothing but minus 3 by 1 minus z inverse. Okay, therefore what you do, you bring this 1 minus z inverse to the left hand side. So it becomes y2 of z minus z inverse into y2 of z. That equals minus 3 times z inverse x of z. Fine. Now bring this minus z inverse y2 of z to the right hand side. So what you have is y2 of z equals minus 3 times z inverse into x of z plus z inverse into y2 of z. That is the implementation given here. That is, if you take x of n, you multiply that with z inverse and then minus 3 because you have minus 3 times z inverse. And then to that you add something which is nothing but a delayed version of y2 of n and multiplied by 1. That's because of the second term here. Add both of them, that is your answer for y2 of n. Is this clear for the second block, h2 of n? For given x of n, y2 of n is obtained using this implementation of h2 of n. Is it clear? Okay. I think it's clear. Great. Finally, what you have is h3 of n. You need to implement the last block. 8 times z inverse by 1 minus 2 z inverse. How do you implement? Simple. X of z is nothing but you multiply that with h3 of z. You get to get y3 of z. Right. That means what? h3 of z is nothing but 8 times z inverse by 1 minus 2 z inverse. So take this 1 minus 2 z inverse to the right hand side. So it becomes 8 times z inverse of x of z equals y3 of z minus 2 times z inverse of y3 of z. So we bring this second term in the right hand side to the left hand side. Why am I doing? When should I bring one term to the other side? So the net result is you should be able to. So the goal is to get the output y3 of n. That means you should have only y3 of n in one side of the equation. Everything else should go out to the other side. See here I just don't have y3 of n. I'll get y3 of n minus 1. That's why any term other than just y3 of z or scaled version of y3 of z by some scalar, I will push everything to the other side of the equation. Only y3 of z should be there in one side of the equation because that is the output that I'm interested to find. Right. So here the second term is z inverse into y3 of z, which is not I'm interested. So I'm pushing this term to the left hand side. So what do you get? 8 times x z inverse of x of z plus 2 times z inverse of y3 of x, y3 of z equals y3 of z. That means what? First I have x of n. I multiply by z inverse and then multiply by 8. I will get the first term in this equation above. Then to this I need to add 2 times delayed version of y3 of n. So basically what I do, I take y3 of n, take one delayed version and then multiply by 2. Add this to your 8 times delayed version of x of n minus 1. When you add both, what you get is y3 of n. Therefore, for a given x of n, if you want to get y3 of n, this is the block you need to implement that implements h3 of z. Is it clear? Okay, great. That's all. Now the job is done. We got h3 of n, h2 of n, and h1 of n. All of them you club to everything put together. This is basically your form. So you have x of n. It's a parallel form 2 realization. So the top block is just it just goes through a multiply by 1. That is, it passed as is. There's nothing. First block does not do anything. Just it passes the x of n as it is. The second block is your h2 of n implementation. That is, you multiply by z inverse and then multiply by minus 3 and then add it with z inverse, the output taken, the sampled version of output, and delaying it by 1 unit and multiplying it by 1. The third branch implements h3 of n. Take the output of all these 3 blocks separately, add them up, you get y of n. Therefore, this entire red box here, implements a filter whose input is x of n and output is y of n. And this is the system that implements the given transfer function using parallel form 2 realization. Is it clear? Okay, great. I guess we have covered all types of filters. So one homework that I would like to give is, take this as a question, okay? And it's a different transfer function. So in today's class, we took one transfer function and we implemented that using all different types of realizations. So take this as your different function, which is h of z is equal to 1 plus 2 z inverse plus z power minus 2 divided by 1 minus 3 by 4 z inverse plus 1 by 8 z power minus 2. Realize this IIR filter using direct form 1 to cascaded and parallel form 1 to structures. So today, actually, with that, this is what I have for today. So with this, basically, the tutorial problem solving for this week ends. Is there any questions I can take now? Are there any questions? Your question is, are there other tools like MATLAB we can learn? Yes, certainly. What you can do is you can implement each of these blocks using in MATLAB. There are tools, but I think at least this signals and systems is a first level course where you learn the theory of it. I think if see the thing with MATLAB is that MATLAB essential not just with MATLAB. If you take any practical simulation, right, simulation software, it can only process discrete time signals, not a continuous time signals. Because continuous time, we don't have any hardware. We don't have hardware whose resolution is infinitely, capable, or whose resolution is infinity, that it can process a continuous time signal. In practice, you only process a digital signal or a discrete time signal. Okay, so MATLAB, if you want to do MATLAB simulations, essentially you need to stick only with discrete time signal. Or if you have a continuous time signal, you have to sample the continuous time signal and obtain its discrete version and process the discrete signal. Okay, so in particular for the realizations that we saw today, you can implement in MATLAB. But since this is a first level course in signal systems, I don't think maybe MATLAB is that necessary to be used. But when you go to a second level course on something like discrete time signal processing or digital signal processing, for everything that you learn, you can always do a MATLAB correspondence simulation. But I think in this course, MATLAB is not a component. Okay, so maybe there are other courses where you can which exclusively will teach MATLAB or something like that. Or the other way is go to MATLAB website. It's called mathworks.com. Let me just write it down for you. It's called mathworks.com. This is the website, official website for MATLAB. And they have a lot of very short courses like on-ramp courses, just to get started, very short courses that will just teach you how to do basic things. So whatever you've learned in the signals and systems, like how to define the frequency, time duration, sampling time, all of that you need to mention. And you can maybe this website has some good amount of small video lectures which explains how to implement different things. Okay, but this is something which for which discrete time signal processing will be more useful, because whatever concept you learn there can be implemented potentially on MATLAB. Okay, so that's the reason in signal systems we don't use MATLAB much, but in discrete time signal processing you can potentially use for every single concept that you learn. Okay, are there any other questions? So one small reminder is that this is the last regular session, in the sense that this course is for 12 weeks and for 12 weeks. But we will be having one final session on 16th April, same time, same link, 6 p.m. and the same link, which will summarize the full course and solve some gate questions from previous years. Okay, a collection of gate questions from all previous years. So that is a small announcement. So please join without fail on 16th April. Yeah, so that's a small announcement. Are there any other question? Okay, then if not, let's stop for today. Let's again continue on 16th April. Or whenever the NPTEL will give you the reminder. Okay, NPTEL will send you the reminder. Please do join. Okay, thank you.